Okay, everyone, hello again. Let's talk about Practice Physics, Chapter 29, Practice Physics from the Katz book, first edition, Chapter 29. So the problems in Chapter 29 from the first edition of the Katz book are found on pages 926 to 933. They comprise, the ones at least that I've chosen to kind of use, they comprise the following. Problems 9, 10, 11, 13, 24, 25, 26, 27, 33, 35, 40, 42, 46, 47, 55, 57, 59, 64, 71, 77, 82, 84, 88, 93, quite a few. I'm only going to do these two problems on film with me talking about them, problems 55 and 71, and try to talk about some of the subtleties associated with such problems, and also maybe look at a situation where we're talking about, maybe expand some of the look that we could give for, let's say, a problem like number 55. But anyway, the goal here is 55 and 71 for the filming, and all the rest of the, and these same problems and all the rest of the problems will scroll at the end the way they look on the PDF document. From there, people are able, if they know how to do it, they're able to be able to get that printed out, I would suppose. It's not the actual just PDF document by itself. It's on the film, but it's a copy of what the PDF document looks like. So whenever you see that in any of the work that I've done, it's a copy of it. It scrolls at the end of the video. So it should be pretty good for you. Let's talk about some of the stuff here. And again, Dr. Katz wrote a great book. This is the first edition of the book that she has that I've been working on for calc-based physics, mechanics, and calc-based physics, electricity, and magnetism. For the stuff that I filmed, very, very much of it has been from the Katz book, the first edition. So, so this kind of catches us up with other things that I had done earlier that are subsequent chapters. Much of this, of course, was prompted by what had happened with the COVID crisis. So we wanted to get a lot of this stuff. We were hoping to get a lot of this stuff on film. I was certainly hoping to do so. Other people have done so as well. Everybody's got their own way of approaching that, I guess you could say. So all the best to everyone, guys. And as we do this, let's work on a few of these problems. As we're looking at this, we can say for 55, I mean, we'll do 55, but before we do problem 55, I guess some general background knowledge. Some general background knowledge of some of the concepts that are in play with problem 55 would be great for us to kind of look at, I think. So we're looking at 55, but before I go into 55 proper, let's look at some things that we can say that are very much of interest. Basically, guys, if you have any kind of a setup regarding a capacitor, a resistor, and let's put an EMF source in there, in other words, a battery. They don't really have, for problem 55, they don't really have the battery in there, so it's somewhat simpler to look at, but very much of the concept of what goes on here is very useful for us. So let's see what we can say. Very much of what I'm going to say in the general sense can be applied in more particular circumstances, more specific circumstances. So let's see what we can do. Okay, they talk about a number of things from pages 9, from Dr. Katz's book, first edition, pages 920 to 924. They talk about some things here, and I'm gonna write them down and erase it, and then kind of come back to it. the amount of charge that's on a capacitor at a time, the amount of charge on a capacitor per unit time, the amount of charge that's on a capacitor for a particular time t, capacitance, potential difference associated with the EMF source, the potential difference associated with the battery, capacitance, potential associated with the battery, the voltage, and then you got something like this. And then there's some things we can do to kind of mess with this a little bit. Okay, I mean, remember that. There's other things to remember, and that's how much charge is on, how much charge is actually on a capacitor at a given time t, given that there's a discharge taking place, there's resistance that has to be overcome while this is discharging, the whole thing in that regard. Okay, so looking at that, you know, we kind of said it. Let's go a slightly different direction and derive a few things, and then attack problem number 55. So this is fine as we got it, guys. Let's see what we can say here. All right, well, I wrote something up there, and I've just erased it. It's going to make sense why I wrote something up there if we say, look, let's say there is some kind of a circuit with direct current going through it, and there is a potential difference across the battery, so it wants to push out those imaginary positive charges, or we'll assume they're positive charges, let's just say that. And we already kind of talked about that subtlety, but it's pushing out the current. And we'll say the current's composed, if anything, of the imaginary positive charges, but it's pushing out the current. The current will get pushed out because of the battery, and then come right back to the battery after it does the whole circuit. Well, part of the circuit is the battery's potential difference. Then there's so what happens with the battery? Well, there's a potential difference associated with the battery. It pushes out the current. Then it runs into the resistor, and there is a potential drop because of the resistor. Then it runs into the capacitor, and there is a potential difference there as well. I mean, it's not easy to charge the capacitor, so it encounters an issue there as well. Well, let's just make this, like I said, 55 is the goal. Let's just step back a little bit and say, if you've got a circuit composed of a battery, a resistor, and a capacitor, well, potential drop, you add all these things associated with potential difference, and by the time it comes all the way around, if you complete the whole circuit, the sum of all the potential drops, the sum of all the potential differences, is 0. Well, the battery is a positive potential difference. It's pushing out the current. The resistor is going to fight, is going to take away, some of that potential energy is, some of the energy that is associated with the movement of the current. It's going to get dissipated by the resistor. It's also going to get dissipated by the capacitor. However much charge Q is on the capacitor at a given time, divided by C. Now, what's going on there? Well, didn't we say C was Q over V or Q over delta V? C C equals Q over V. V equals, multiply by V on each side and divide by C. That's your Q over C. That's got to equal 0. Okay. So there's potential drops associated with what's being accomplished. To accomplish getting past the resistor, there's a drop in potential. To accomplish charging a capacitor, there's going to be a drop in potential. It takes work to charge the capacitor. It takes work to overcome the resistor. That's why these two are minus. You got the E right here. Okay. All right, we said a few things. Let's keep going. Well, what do you say? I mean, you look for maybe a way out here. This is Q. Do you guys remember that I is dq dt? Makes things somewhat easier in terms of differential equations because you've got the language of Q showing up in place of some other item that doesn't, at first glance, you're not really maybe associating it with Q. I equals dq dt. Yeah, I agree, it does. I equals dq dt. So I'll tell you what we're going to do. I equals dq dt. Absolutely true. Tell you what, let's, I guess the one that's got the derivative in it has got an integral in it somehow. If we're going to talk about an amount of charge. There, if it's a dq dt, if I were to integrate dq dt or do something with it, perhaps there's a number of things that show up just by virtue of the fact that it is a differential divided by a differential. It is a derivative. If that's the case, why don't you solve for dq dt and see if we can, maybe have a conversation about various things and maybe we can draw various conclusions as well. Well, okay, I mean, the way to look at that would be, why don't you add a positive dq dt r on each side, add a positive dq dt r on each side. So add a positive dq dt r on each side. So you got dq dt r over here, and then you got the rest. So this is all, you got it out of there. It's E minus, or epsilon minus, looking something like that. True. Why don't you divide by R on each side? Doesn't matter what side you put something on, just make sure you're mathematically consistent. You got E over R minus Q over RC. True. Yeah, I mean, I wrote it a little differently when I wrote it last time. It doesn't matter. We're going to get to the same conclusion here, guys. Tell you what do you say? What do you say you multiply one of these by a special one called C over C? And that's Q over RC here. And that comes out to this. dq dt equals EC minus Q over RC. Yeah, that's true. Tell you what, I mean, what do you got? What do we know? Well, look, Q is the only variable here, and so is time. Time's a variable, and charge Q is a variable. The battery with potential difference epsilon or E with this, let's just call it, well, I'll call it epsilon or E. It looks like an epsilon to me, guys. The potential difference of the battery is constant. It's epsilon. The potential difference of the battery is constant. It's epsilon. The capacitance of the capacitor is a constant. The resistance is a constant, and the capacitance once again is a constant. So epsilon, C, and R, those are all constants. Q varies, and dq dt is going to vary, and it's going to vary with time. What do you think? Well, I tell you what, I think, let's see if we can put something together here. What do you say you take this entire top and divide by that entire top on each side, and then take this dt here and multiply by dt on each side. So basically what you're going to do is you're going to divide by the quantity epsilon c minus q on each side, and after you're done doing that, you're going to multiply by dt on each side, and you're going to end up getting dq dt over Rc. Okay, once again, you took this quantity on top, the numerator on top right here. You took that numerator and you divided by that numerator on each side of the equation. After you've done that, you'll multiply by dt on each side of the equation. And that gets you here. That's a very important conclusion. Once you get there, guys, it's a very important conclusion. So, you got this right here. I'll tell you what. Let's see how this stuff behaves. Well, I'll tell you what. What do you say you integrate? There's no charge initially on the capacitor in this scheme. No charge initially on the capacitor, and you're going to get it to have a charge Q on it, some charge Q. Well, why don't you integrate appropriate sides? You got dq over C epsilon minus Q. And here you're going to integrate. While that's happening, it took a time t for that to happen. It took a time t for the capacitor to reach a charge Q. It took a time t for the capacitor to reach a time Q. So it went from 0 to t. Absolutely. Very important. What the heck is it? Well, once again, there's a lot you can say. There's a lot you can say. There's a lot you don't have to say. If you're going to call CE minus Q, if you're going to call that U, then du dq, these are constants. C is a constant, epsilon's a constant. Q is variable. Du dq is -1. du equals negative dq. So, sounds good to me. If du is equal to negative dq, you could say, don't worry about the limits of integration, just try to get the antiderivative here. If dq is what it is here, dq is dq, yeah, du is negative dq. So in other words, put another way, dq equals negative du. So we got a negative du. This whole thing, u is that whole thing. Well, that's just the u right here. If you're going to integrate that, you're going to put the -1, the product -1 over there. So negative ln u is the, well, good. I mean, well, what was, you know, if negative ln u is what it is, negative ln u, that's simply, at the end of the day, the integral here before you go between the limits is negative ln c epsilon minus q. Okay. So that's kind of what's going on, guys. This one right here is a constant on the bottom. It's 1 over rc. Well, the integral of 1 dt is t. The integral of 1 dt is just t, so it's t over rc. You're going to do that. So what's going on here? Well, what we got here is negative ln ce minus q evaluated between 0 and q. And the other thing here is take 1 over rc out of there, do the integral here, you get t. You basically got t over rc evaluated between 0 and t. Well, this should be somewhat, you know, hopefully somewhat convenient the way it all comes out, guys. So you look at it. Well, okay. Let's put the q in there. And that's, well, I mean, what we got? We got negative ln ce c epsilon minus q minus, put a 0 in here, minus a negative ln ce. Okay, what's going on here? Put a t up here, you got t over rc. Put a 0 up here, you got a 0, so no need to go any further. So we got, we're not done, but at least we got to here. Let's see what we can say. What do we got? Minus a minus is plus. You got ln ce or ln c epsilon. I keep calling it e. Let's call it e. What the heck? A positive ln ce, but this negatives you're adding. It's all addition. You know, minus this is, you know, plus the opposite of this. So that's a positive and a negative. It's like subtraction. So maybe it's a little easier to look at that way. So plus a negative or just minus ln CE minus Q. So let's just quickly see that. Right, exactly. And that's going to be equal to T over RC. Okay. Sure, a lot you can say here. Plus, yeah, there's a whole lot you can say. Let's say, you can play it a bunch of ways here. Multiply, maybe you'll see the justification for this in a little bit. Multiply both sides of the equation by -1, and then it ends up, the order of the subtraction ends up reversing itself. If you multiply by -1, yeah, I know, true, but if you multiply by -1, you multiply by -1 on each side. So what do we got? So you multiplied by -1 on each side. So the order of the subtraction got reversed. Here, and then we multiply by -1 on each side, as we said, the order of the subtraction gets reversed, and multiply by -1 on this side as well, as we said, it's a negative T over RC. What's going on? Well, there's a reason for it. Maybe it's a little easier to look at, guys, if for no other reason. The difference of two logarithms is the logarithm of the ratio. So we got that. True. My goal is to get some kind of solution for T, get some kind of idea how this thing... Now remember, this all happened while we were charging up a capacitor. So the Q that we get will be an equation saying that Q is the charge that is the amount of charge that is going on to the capacitor as time goes on. So as time goes on, a charge Q is appearing on the capacitor, or at least is going onto the capacitor. So let's have a look at what's going on here. That's the amount of charge Q that's gone onto the capacitor. Let's see what we can say. I mean, there's some real subtle points that can occur, guys, so we got to really watch it here. Okay, let's see what, then we'll draw, let's solve for Q. Now, Q is a fluid situation. The more time that passes, the more charge we have on the capacitor. So as charge is going on to the capacitor, that's very important. So what do we got here? Well, if two things are equal, they remain equal if you do the same thing on each side. And there's a lot going on here. It's always quite the argument as to what you want to do with this. Yeah, let's leave it as is for now. Okay. If two things are equal, if two items are equal, Then if you do the same thing on each side of the equation, it remains an equation. What are we talking about? Well, we got you'll see what I'm trying to say in a second. All right, these two are equal. These two are equal, so if you put each of them on top of E, they're still equal. So E, if you exponentiate each side, if this and this are equal, and we said that they are, then each of them on top of E means that whatever happens, they're still both equal. The exponentiation base E of the natural logarithm of something is just the original something that was within the logarithm. Say that again. The exponentiation of the logarithm of something, if you exponentiate the natural logarithm of something, you get the something. If you exponentiate this, it remains this. So we got that. So we got this. Now let's do it. Let's solve for Q. Multiply by CE on each side. Here's what you're going to do. You're going to basically multiply. You're going to multiply by CE on each side. Then after you've done that, the result you're going to take over here, subtract that entire thing. Well, let me look. This is more. By the time I explain it, I might as well just do it. Multiply by CE on each side. And you got this. Subtract CE, e to the negative t over RC on each side. E to the negative t over RC. Minus Q equals 0. Add a positive Q on each side. Q equals e to the negative t over RC. So, as we proceed, we are looking at a situation of how something charges as time goes on. The bigger that t gets, the bigger that t gets, a big T divided by RC is still a big number. A big positive number multiplied by -1 is a very negative number. E to the very negative number approaches 0. As time gets bigger and bigger and bigger, this whole function, the functional value as t gets bigger and bigger and bigger, This whole functional value goes towards 0. 1 minus something close to 0 is the entire charge that would be on the capacitor if the capacitor was fully charged. At the time t equals 0, 0 divided by RC is 0. E to the 0 is 1. 1 minus 1 is 0. There's no charge on this thing at time t equals 0. And as time goes on, it keeps getting more and more charged until it approaches the maximum charge of the capacitor. So what you have is we got C equals Q over V. Q equals CV. The V is the same as this E, the electromotive force associated with the potential difference associated with the battery. In plain English, this is the potential of the battery. V and E are the same thing. And this is the maximum charge you can get if C equals Q over V. If C equals Q over V, you guys. Or if C equals Q over V, or C equals Q over E. And E is the same as V. So CE is going to be the maximum Q. All right, that's the conclusion. This is the charging of a capacitor. For charging up a capacitor. And some of what went in to get it. So, the amount of charge on the capacitor when the capacitor is charging the capacitor in the circumstances that we've described. For charging, we're talking about Q equals So it's saying that. Yeah, absolutely, for charging. When we're talking about charging. What about how much, so this is what's on, Q is the amount of charge on the capacitor. Small q is the amount of charge on the capacitor, or capital Q, whatever Q you want to call it, but we started with small q, so that's what we're going to use. Q is the amount of charge on the capacitor plates. Q is the amount of charge on the capacitor plates at time t while the capacitor is charging. If it's discharging, what is the amount Q on the plates? Well, it's an interesting point in its own right. It discharges the same way that it charges, in a sense. I mean, there's a lot to be said regarding that. So, see how was there another way we had? you can say a few things. First of all, let's talk about the flow of charge going on to the capacitor, or the flow of charge in general when there's a capacitor and resistor present and an electromotive source for potential difference, epsilon, the voltage V is equal to E, the capital E. Can we say, is there a current? We said the charge, and to be even more exacting about it, I guess you could say, what do they say, guys? If it's not broke, don't fix it, right? Let me see here. So Q in relation to time. So what does this thing equal? What's the rate of flow? Here's charge. What's the rate of flow of charge? Well, we already said that. We already said that it was dq dt. Said it was dq dt. dq dt of this right here, this is the QT. Let's take the CE and multiply it throughout. Yeah, we said that. That's Q, and I'm going to get from here, when you write as large as I do, you never have enough room. So let's see what we got here. We got this. dq dt dq dt, and that's going to equal d dt of this. So let's see here. I just need more room, guys, is what I need. When you write as large as I do. I just want to make sure you guys can see what I'm doing. And that usually means I got to write I want to write very loudly to get this thing under control completely. So you got this. Okay. The derivative with respect to time of a constant is 0. The derivative with respect to time of this is going to equal the negative CE times the derivative of this, and the derivative of this is e to the negative t over RC times, by the chain rule, the derivative of what's going on up here, which is negative 1 over RC, and there was also a negative 1 right here. Okay, let's be extremely careful. And the CE was present as well. So let's see what we got here. What we had is the CE was right here. That was the negative CE. Okay, let's try that again. d dt of this sum, because it is a sum, it's CE plus a negative CE, e to the negative t over RC. Okay, well, the derivative with respect to time of a constant, this constant under consideration is c times e. The derivative of the constant, the derivative with respect to time of the constant ce is 0. This is plus a negative ce, e to the negative t over rc. The derivative with respect to time of this is the constant negative ce put out in front, multiplied by the derivative of this quantity. The derivative of this quantity is itself times the derivative of the quantity negative t over rc with respect to t, and that's negative 1 over rc. So there you go. So you got that right there, and I think that's it. I think that's how we got it. So we got this. What is a negative times a negative? It's a positive answer. Let's try it again. A negative times a negative is a positive answer. Yeah, there's your answer. And that's what I is equal to. So I sub t, or just I, and q, I of t, or just I, and q of t, or just q, is how we can say all this stuff. The c's cancel. You got E, voltage divided by R is current. It's the maximum current because this right here strives to get there, I guess you could say. As it's charging. So, I of t, the way they write the stuff, yeah, voltage divided by resistance is a current. This is actually a big number, relatively speaking, because this thing makes the I of t smaller than E over R. This is the biggest it can be. As you go toward infinity, you will reach this. That's the maximum current, E over R. So that's pretty interesting. Even here, this is the maximum charge that can be obtained. Yeah, but it's, you got to have this just be 1 and all that be 0. And this strives to get to 0 as you go toward an infinite amount of time. But this is the maximum charge that's present. So you see what those two are. I mean, when you look at them, you've got this, and you got this. Now, is there, like I said, can you use the language of E over R is maximum current, and CE is maximum charge, and it gets written, I mean, I don't know, I wrote in different ways. The book itself, may use a little different symbolism. That's neither here nor there, you guys. We know what we need to do. I mean, just make sure you're agreeing upon what's what. So when you do this, that's true. It's about as simple as that. So what you got is Q of t, the CE is the maximum charge, Q max, 1 minus and the I of t. So the Q of t is this situation where the Q max is equal to CE. The I of t is this situation where the I max is E over R. Okay, not too bad. Got this, got that. And now what happens if it's and that's for charging. This is all associated. All of this is associated with charging. What happens if there's a discharge? How is that associated with the whole situation? For a discharge to occur, you're talking about, they're kind of a fascinating matter in its own right here, guys. You're saying that this is how much charge is there. If you were to reverse this, it will reverse completely the same way. In other words, if it took a particular amount of time to charge up to a certain amount. It took a particular amount of time to charge up to here. What are we talking about the other way of saying if it was discharging? So there's different ways they kind of go there. And there's different ways this can be written all over the place, actually, the way we got it. So they talk about discharging a capacitor. And they talk about in problem 93, and I go into that a little bit. For problem 93, maybe we could talk about it now a little bit. In problem 93, we're going to show about discharging. We're going to show that for a discharging RC circuit, the charge Q of t on the capacitor as a function of time is going to be something a little easier to look at, and the IT is going to be something a little easier to look at. Well, the functions are mere reflections of each other in a sense. So that's something of great interest. We want to talk about something like that. So how are you going to say this? So this is the charging of it. What I did for 93, let's kind of do this a little bit. So we had the battery in there. We did the stuff we did. We're assuming there's no battery. You're disconnecting the battery, and then from there you're kind of playing the game. There's some interesting conclusions that can be drawn here, guys. Let me talk to you about it. It's in a backhanded way. Well, not too backhanded at all. We're literally doing a problem like something like a problem 93. How you actually do something like this? Okay, so. We looked at it, we got some stuff here. The conclusions are true, we got the notes for it, so we're not going to worry about that. And Okay, you're playing essentially, guys, with the same differential equation of the past. You know, but you got to remember, there's not going to be, we're going to assume no battery here because the capacitor is charged, you've disconnected the battery, and now you're going to let the capacitor discharge, and we're going to see what we can say about it. We know, associated with problem, and you'll see this in the notes as well, guys, associated with problem 93, you go E minus IR minus Q over C. We're doing something very similar to what we've already done, guys. You got E, you got IR, you got Q over C. True. Let's get both these over there. And we got E is equal to, let's add a positive IR on each side. Let's add a positive Q over C on each side. We got this. The E, the epsilon, the E equals 0 because it is assumed no battery nor any other EMF source attached. So you got this. True. If that's true, why don't you write the I as dq dt times R plus Q over C. All right. Why don't we get this, you know, why don't we get this over there and kind of just reverse the order that we're writing it. Make a long story short, guys, we got this negative Q over C. Let's divide by R on each side. True. Let's multiply by dt on each side and divide by negative Q on each side. True. Let's take a good look at this thing. Usually, you know, I've been using negative time here, so let's do it again. Let's multiply by negative 1 on each side. Multiply by a negative 1 on each side. True. That's the same as saying, you know, negative dt over Rc. Negative dt over Rc is just, negative dt over Rc is just negative 1 over Rc times dt. You're starting from a maximum Q. The battery's been disconnected. You've more or less, very, very close to, for all practical purposes, you have charged the battery, you have charged the capacitor fully. And so you've got Q max, and you're going to make it fall down to a Q. Okay. That's going to take place from a time t0 to a time t. This is a lot of what we've already done, guys. A lot of the math is very similar, some ways less complicated. So you got this going on, guys, right? Do the integral here. ln Q evaluated between Q max and some Q. The Q is smaller than Q max. Max is the biggest. Integrate this. you end up getting negative 1 over RC dt, that's a constant, dt, that's negative t over RC evaluated between 0 and t. What you get here is you get the difference of two logarithms. ln, you get a lot here. I mean, we can figure out how we want to talk about it. You get ln q evaluated at q minus ln, so ln at q minus ln at q max. The difference of two logarithms is the difference of two logarithms is the logarithm of the quotient when done correctly. That's negative t over RC. That's just 0. Negative t over RC minus 0 is just this. Let's exponentiate both sides. Let's take both sides. Two things are equal, they remain equal if you exponentiate each side. You get q over q max you get q over q max equals E and that's it. Yeah, it's absolutely true. They call RC, in all instances, they call it tau. That's the time constant. There's a tau under here. So it gets written, I mean, you can see it written a lot of ways. You can say Q equals Q max E So you got that. So there's a lot of ways to write it, guys, but I mean, this is the big thing. Well, I don't know if that's interesting. How would you write the rate of flow of charge, rate of flow of current in that regard? Go dq dt. You know, I would be equal to dq dt. Absolutely. It's dq dt. So what would you get? You'd get the Q max. So we're going to have to see how you'd actually want to write that. You'd write like this. That's the Q max, guys. And this thing comes out to Q max, and we're going to discuss it some. You got Q max E to the negative T over RC times a negative times a negative 1 over RC. Well, what's going on here? I is going to equal Q max times, this could be a negative. Here's R, here's C, and negative T over RC. RC is tau, whatever. That's no problem. What is Q over C? Q over C is voltage. Q divided by C is voltage. Then you got voltage over resistance. That's current. So that comes out in terms of current, comes out to the maximum current that you could have. With a maximum voltage divided by R is a maximum current associated with it. And it's negative. And that's the case. So, pretty fascinating how that works out. They are mirror reflections, one of the other. How do you know that they're mirror reflections, one of the other? What I did earlier. We could say for the charging, for the discharging, let's kind of summarize it in that sense. Okay, you see what we got right there, guys, how we did it. Again, it was, the whole thing was Q max over RC, or CR. Well, this thing right here, Q over C, you know that C is Q over V. V is Q over C. V is Q over C. Q over C, that's V. Then you got V over R. That's associated with a current. How much current? It's a maximum current because this is a maximum charge. Maximum charge divided by a particular capacitance, this being the biggest number possible for charge, maximum charge divided by a capacitance is the maximum voltage that you can have. Well, the maximum voltage for a given resistance is going to give you a maximum current. Now, we said there was a negative in there. The negative's got to come out in front, throw the negative on there, and you got that. The two scenarios of charging and discharging, there's a lot, they mirror one another in a sense. What do you mean? Well, you were charging this thing, and you got something here. So you could say, this is a little bit of a little freelance here, I guess, at some point. So we said we have all this, and this is for the discharging when we did all that. So it's a question of reference frame. But if you work this accurately in terms of the reference frames, you're going to see something very interesting. The mathematics should be rather, will illustrate something, I think. And tau is the time constant and everything else, and it depends how far you want to go with this when you're saying some of this stuff, you guys. But we ended up saying that there was a charging scenario with the battery, and we modified how we wrote it. There was a charging scenario, and then there's the discharging scenario. And there's tremendous similarity in the look, and there's tremendous similarity in terms of the symmetry of how this all happens. What you can say is we ended up, for the charging scenario, guys, we ended up saying we did some stuff when it was for the charging scenario. We said we looked at it, and now to save my life, I can't find it. Okay, here it is. Right. We tinkered with everything. We did all the integrals and stuff like that, and at the end of all of it, we ended up getting, when you're charging it, we got Q was going to equal, so what we had was, we did all the integral that we had to do and stuff, and we ended up getting CE minus Q over CE. CE minus Q over CE, the natural logarithm of that, when we had done the earlier work, was equal to this. True. We exponentiated each side, set them equal to each other. CE minus Q, we set them equal to each other, multiplied by CE on each side. Solve for Q, and we got CE 1 minus e to the negative t over RC. It's absolutely true. This CE was the Q max. That's Q. That's this. Yeah, that's true. If you take, you can write Q max a lot of ways too, right? I mean, but you got, if we do this, we said something about the other one. When it's charging, when it's discharging, we said we were going to have this for an answer. Q max again, simply e to the negative t over tau, over RC. Saying, okay, yeah, we already talked about all this. Maybe change the symbols a little bit. We've changed the symbols a little bit. There's a lot of flexibility in how we can write things. RC is tau, but we already said this. Big deal. Yeah, but there's so much symmetry, and we derived both. Using calculus, we were able to derive both. But I got a question for you. If you look at, if there's so much symmetry here, in both scenarios, they got to add up to the maximum charge. In other words, whatever location, whatever the Q is for the discharging, what's left over? I mean, you could look at two scenarios here, guys. You could say, this is Q, the amount of charge that goes onto the capacitor while the charging is taking place, the amount of charge that's present on the capacitor at a time t, the amount of charge that's on the capacitor at a time t while we are charging the capacitor is given by this formula. The amount of charge on the capacitor while we are discharging it is given by that formula. True. Whatever's on the capacitor when you're discharging and whatever's on the capacitor when you are charging. In other words, this is the amount of charge present. If you add it, there's kind of interesting mathematics here. If you just took this quantity, this entire quantity here, and added it with this quantity here, you'd get Q max. They are mere reflections of one another. In other words, if this is if this is the amount of charge on the capacitor plates while we are charging the capacitor, if this is the amount of charge, this is the amount of charge on the capacitor plates while we are charging. While we're charging, bam, at a set instant, this is so much charge is on the capacitor plates. Well, that's the amount of charge on the capacitor plates. When this much charge were to leave a full, so this is the amount of charge on the capacitor plates as you're charging it. Oh, you reached up to here. You didn't go T, you didn't go toward it, you didn't go T equals infinity or T equals something very big yet. You could, but you didn't quite yet. And this is the amount of charge you got on the capacitor plate. Okay, great. If this much charge had left the capacitor plate rather than being on it, and it was fully, and let's say it was fully charged before, this is fully charged before. This is fully charged before, and I'm going to subtract from the fully charged that it was, from the fully charged that it was, this much left, leaving you an amount Q that's on the plates while it's discharging. You got Q max amount of charge initially. I'm going to show you that's the answer. That right there. I'm going to start with this. Let's say you're charging a capacitor. You're charging it, you're charging it, you're charging it. You might charge it completely fully charged. Then it's at Q max. Okay, I get that. How much is on a capacitor plate at T equals 0 if you're about to discharge it, if you fully charged it? Well, it's Q max if you fully charged it. How much is on the capacitor plates when you're beginning to charge it? And you have a T equals 0. You haven't charged anything on it yet. Then Q is equal to 0 when you're charging it. I'm saying to you, if this is the way something charges, it's also the way something discharges. They're mere reflections of one another. The book does a great job. The curve, so to speak, is identical. The functions are, in a sense, very, very symmetric one to the other. They're very, very symmetric. You could say, looking at it, with all present, I mean, they really got that look, guys. They've got the attribute. There's tremendous symmetry there. I don't want to say too much more unless I were able to sit down and rather than just look at this on the fly, analyze it a little more strictly. But I do want to say this. This is how the thing charges. This is how the thing charges up. Great. Great. There is a point where where it's charging up, that this much has actually left it. In other words, let's say you're starting from scratch and now you're discharging. Q max is what it is. So what happens is, if this is how you proceed to charge something up, to discharge it, it'll discharge with the same kind of rate. That's the discharge rate. So you take the rate at which it's discharging, you take the way, it'll charge up just like this, but it'll charge up just like this, but it'll also discharge just like this. Yeah, what's left then? Well, what's left is you had the maximum, and then you lost this. You're losing this. What's that? Well, it's Q max times 1. That's Q max. Q max times this. Q max minus Q max is out of there. Minus a minus, it's no accident. That's what's on the plate. If that's what is on the plate, what's off the plate? If this is on the plate, see, this Q is a little deceptive. It's not the same. The Q is Q. I get that. Okay, the same letter. I get it. This is the Q that is on the plate after things leave. This is the Q that gets on the plate when things are coming onto it. This that is on the plate is equal to the maximum amount of charge minus an identical rate of leaving. Minus this in a sense, which means that, okay, what's going on? What do we got here? How is this thing leaving? It leaves the same way that it got on. In a sense, or at least mathematically, the aggregate of what's going on there is what it is. So what you have is, this is the rate. This is the rate at which it's leaving. This is just like this right here is the rate at which it's going onto the capacitor. This is the rate at which it is leaving the capacitor. Put better, this describes not the rate as much. The rate would be dq dt. I mean, that's the big thing here. If you go here, if you went for the charging, if you did I equals dq dt, do all the mathematics here, what happens? Well, it's Q max times 1, that's a constant, the derivative with respect to time. dq dt dq dt, or dq dt is d all this dt. D of this right here, a constant dt, is 0. Here, it's going to be negative. You've got a negative. Let's see here. You got negative q max. This guy, it stays as is, and the negative comes down. Negative q max, and a negative this is going to be q over RC. Well, wait a minute. Q over C is voltage, maximum voltage. Maximum voltage divided by R is I max. I max E to the negative T over RC. True. As time goes. Here's all this. Go dq dt, go dq dt, go d all this dt, and you get I is equal to, here we go, the negative 1 over RC comes here. So let us just see here, guys, just to be sure. Right, it's going on to there. Negative Q, negative RC, right. This one will be this, Q max over negative 1 over RC. Q max times negative 1 over RC is negative 1 over is negative 1. So what you have here, guys, you'd have Q max, the negative RC right here. Well, negative Q max over C is negative V max. Negative V max divided by R is negative I max. So what we have here is negative I max E same numbers, guys. But yeah, it's got to be a negative though. So don't want to erase anything here, guys. But I mean, you got associated with this, you got the I equals negative I max. It's going in the other direction. It's exactly going in the other direction, the same rate, the same way that it was going the direction contrary to that. Yeah. It's the same exact. Are they the same numbers? Yeah. The rate at which charge is entering is the same rate at a given time at which it is leaving. Only it's going in the reverse direction. Here, charge is being lost per unit time. Charge is accumulating at charge is traveling to the capacitor at a rate dq dt, which is I. It is traveling, charge is traveling to the capacitor, onto the capacitor. The current is going at a particular rate, at a particular time. The current is flowing in such a manner that the change in the Q, the change in the charge accumulated per unit time is happening at this rate as you are accumulating charge onto the capacitor plate. As you are leaving the capacitor plate, so here If you're charging the capacitor, you're gaining charge at this rate. You're gaining charge at this rate if you're charging the capacitor. You are losing charge at the exact same rate, that's why the negative is here, when you're discharging the capacitor. At any given instant, it's as simple as that. It's maybe one of the easiest ways to say it. So in other words, you're also losing charge. Charge is present away from the capacitor like this. Okay, we'll take that amount of charge away from what was initially present because we're discharging a capacitor right now. When you're discharging a capacitor, this is the amount of charge that would have been on the plate in a period of time. But now, when you're charging, certainly this is the amount of charge that's on the plate after a certain period of time. When you're charging, and you are charging it up at this rate. And this is the amount of charge on the capacitor plates as you're charging the capacitor. Sure. This is the exact same number for a given value of t as it is over there, but this is the amount that's left. This is the amount that got on to the plate. This is the amount that left the plate. Well, what's left over? When you're discharging, this is what's left. This is the leaving when you're discharging. This is the accumulation when you're charging, and this is the rate of accumulation when you're charging. This is in the discharging, however, this is what's leaving. When you're charging, you're accumulating like this, and you're accumulating at this rate. When you're charging, when you're discharging, that same amount that would have been going on after a time t has left, that amount left, the same amount that would have gone on in the charging scenario, in the discharging scenario, the same exact amount left. Well, what's left? What's left is you had it fully charged, and then you started discharging. Here's fully charged minus all this. Okay, if I do the math, I look, I get to here. And that's where that right there, which is the same as this. It doesn't really look, I mean, there's a lot of similarities here. That's interesting. This is what you would have on, and this is what you do have on after this much left. And together they got to add up to Q max. Q max times this plus Q max minus the same amount as Q max times this. Add this and this. Forget the Q's right now. This is what you would have on the capacitor when it's charging, and this is what you do have on when it's discharging. What's the difference? This amount that you would have had on when you were charging, when you were charging the capacitor, this is the amount that you would have had on in a time t, and it's charging at this rate. At least the flow of current is moving like this. Sure, when you're charging, flow of current moving like this, this is what you would have on after a time t if you're charging. True. If you're discharging, that exact same amount that came on in the charge, in the charge scenario, in the discharge scenario, that exact same amount left. You had Q max to begin with, and you lost all this. Well, wait a minute. These guys cancel out. This minus this out of there. So this minus this out of there. Because that's the times the 1 right there, guys. Should be pretty obvious. I mean, what happens is, this times this is Q max. Q max minus Q max is 0. This times this is that scenario, the negative of it. Well, the Q max minus Q max was 0, so this and all that is gone. And then you got, so you're going minus this, takes out that one. Minus this is minus a minus, is plus that, times this. So a better scenario, I'm sure you guys know this, forgive me for not ending this 20 minutes ago on this, but just in case there's an issue. I mean, you got Q here, you got Q max here, minus what? all of that goes here, goes there, and then you're going to subtract all that. Minus Q max, that's this, right? I mean, this is this guy. Q max times this, Q max times that, minus Q max that's simply just distribute all that out. It's Q max minus Q max. Q max minus Q max minus a minus is plus Q max. Okay, I hope this is visible on the stuff, guys. That and that are gone. You got Q max e to the negative t over RC. And that happened from taking Q max and subtracting this. Subtract right here, from where my hand is here to here. Subtract this from Q max, and you get this. And notice when you add them together, you're going to get Q max. Sure. There's a mere reflection here in a sense, if we're careful about it. And the symbolism can sometimes in the symbolism we can get lost a little bit. Same thing here, guys. You took the first derivative of this and you got the same exact magnitude. It's discharging at this rate. Here, this is the amount that is on the plate. This is the amount on the plate after a discharge occurred. But after a certain amount of time, this much actually left, which is the same amount for the same amount of time that would go on. This much would go on after time t, but this much would also leave after time t if it was fully charged. And it would leave at the exact same rate, but it'd be negative here because you're losing. You're not accumulating charge there, guys. You're losing charge. Exact same numbers here. This ain't the exact same number because this is what's left on the plates. What is left? This is what is left on the plates. What has gone away? This is what's left. What has gone away? Right here. This is what's gone away. It's the same thing as that. Okay, so we got the numbers. The book does a great job on it as well. It's so many ways you can talk about this stuff, but it's a good way to look at it. And the math is true. The math works out when we actually do it. All right, it's got some elements of some other problems that are to be found, guys. So okay, let's see for number 55. Okay, so 50, we said all that. Let's kind of just answer their question regarding 55 and see what we can say about that. All right, so given what we know, they're saying a 650 ohm resistor is connected across the terminals of a 12 nanofarad capacitor that carries an initial charge, a maximum charge, so I guess we assume it's a maximum charge, A 650 ohm resistor is connected across the terminals of a 12 nanofarad capacitor that carries an initial charge of 7.40 microcoulombs. What is the magnitude of the maximum current in the resistor? That's A. B. What is the current in the resistor 5 microseconds after the circuit is completed and the capacitor begins to discharge through the resistor? C. How much charge remains in the capacitor 5 microseconds after the circuit is completed? So, that's kind of where we're at, guys. They're saying, for this one right here, they're just saying it's a 650 ohm resistor. It's connected across the terminals of a 12 nanofarad capacitor that carries an initial charge of 7.40 microcoulombs. A, B, C. A, what is the magnitude of the maximum current in the resistor? Fair enough. B, what is the current in the resistor 5 microseconds after the circuit is completed and the capacitor begins to discharge through the resistor? C, how much charge remains in the capacitor 5 microseconds after the circuit is completed? So a good amount of things asked for us there. This is a lot of what we've already said, guys. We talked about it in a very general sense. We know the deal. We've been there, guys. We've seen all of this. We're assuming maximum charge. I mean, the way it's stated is not quite obvious, but we're just going to say this. I max is going to be the maximum potential difference over the resistance. Well, what is Q max divided by capacitance? Isn't Q divided by capacitance voltage? Q divided by capacitance is potential difference. The R is here. Q divided, maximum charge divided by capacitance is maximum voltage across the capacitor. Maximum voltage across the capacitor divided by R is indicative of the maximum current, maximum flow rate of the current that's going to take place. Let's make the long story short, guys. They're telling us Q max is 7.4 times 10 to the negative 6. 7.4 times 10 to the negative 6, 7.4 times 10 to the negative 6 coulombs, or 7.4 microcoulombs. The resistance is 650 ohms. The capacitance is 12 nanofarads. We got it. The maximum is going to occur when the charge is at a maximum and it starts to discharge. That makes sense. Because if you look at it, you're looking at something of this nature. I max e to the negative, t over RC. Well, if t is equal to 0, that's going to be your biggest answer, and that's your I max. So it makes sense. The flow rate of the current, the flow rate of the flow rate of the current, the flow rate of the charge, how the charge is moving. Pretty much synonymous, depends on the context in which you say something, I guess. There's A. That's A. B. How much current is flowing at that moment? Well, we just figured out the max current, guys. The max current was this. This is I max. That's I max. E to the negative t. Negative t, they're talking about microseconds, aren't they? Micro is this. 650 is this. Might as well multiply it out and just have the tau. That's the tau anyway, right? The 7.8 is the tau, guys. You get the 949. That's -5. It's a fascinating point here, guys. Yeah, that would make sense. 7.2, 7.8. Okay. Yeah, it's not quite the what you got to watch. Be very careful here. This right here. Let me just see what I could say here. Yes. 7.2 and half of that. Yeah, 7.8. This right here, if you made it smaller by 1,000, this would be 7. The tau would be 7.8. 7.8 times 10 to the -6. If you so be careful. They don't here. I canceled 10 to the -6 and 10 to the -6. That's why I got that. That's not really the tau. It points toward where the tau is. You multiply these two, that's the tau. You got to have 10 to the -6 in there as well. 7.8 times 10 to the -6. Okay. Whatever it is, you get, and you'll see it in my notes as well, guys. It's going to come out to 4.998875 amps. Man, that's awfully. That's pretty close. They give it as 5 amps and they're done. You are losing charge, however. What is the rate? Remember, this thing's discharging, guys. So you got to put a negative on there. Okay. The way it really was, honestly, what do we say it was? It's I equals negative I max e to the -t over RC. Okay, I don't quite have it like that in the notes, but in the end we write it there. We've seen how they write some of the work here, and you've seen it in the notes leading up to this. That's B. It's got to be -5 amps because losing charge. So it's -5 amps. And the key, I said I equals 0.5A, and the key says -0.5A because capacitor is discharging. So what's the magnitude? Are they saying magnitude here? What is the current? No, they're not saying the magnitude of the current. So you got to put a negative on there, guys. So I kind of tried to discuss the subtlety of it a little bit. How much charge remains on the capacitor after that has occurred? Well, you could integrate the current and find out how much has actually gone through. Yeah, that answer is already given to you. It's called Q equals Q max times the quantity 1 minus e to the -t over RC. That is what within the right limits. If we're looking at something like that, it should be giving you something like that, like what's on there. It's if you were actually charging it. So or how much leaves. 0 at a time t, yeah, you'd be getting basically what this tells you what's on the capacitor as it is discharging. This tells you what's on the capacitor as it is discharging. How much is left? Well, it had, this tells you how much is left on there. This tells you how much is left on there, and true, and how much is left. How much is left is Q max is the maximum minus this. You got to remember the amount that left. If this is the amount that's on, ladies and gentlemen, this is the amount that's on, then the amount that left is the huge amount that was initially on there. This is the amount that remains. This is the amount that remains on there. Well, how much is left? Well, this is the amount that was on there. You're only left with this amount after something left. So how much left? Well, take the amount that remains on there, this, Q max e to the -t over RC. This is what's left on the capacitor. This right here is what's left on the capacitor at time t. And this is what it was before you started discharging. The difference between the two, what's left and what was on there, and what is not, but I say what's left, what remains. This is what remains. This is what remains on there. If you have what remains on there and you take away what remains from what was entirely there at the very beginning, the difference between the two, this is what remains, this is the maximum that was there. The difference between the two tells you Qmax minus Qmax. Well, this argument is something we've beat up pretty good. I mean, you got Qmax, factor it out of there. That's 1 minus. That looks awfully familiar. Yeah, that's what it is when you were charging it. And as we said, there's mirror reflection here of what's going on. So this is what you're going to answer for C. You're going to put it on there, and you're going to be okay. So let's see here. How do they say it? They just said, how much charge remains in the capacitor after it's completed? Okay. There's a lot you can say here. You multiply. The same exact thing happened here. I did a little more. I took this one. I took that one right there, guys, and I got an answer for what's left, and I took it away from the other one. So in other words, we said this. No, so what remained. They didn't say what left, actually. So it's easier than I thought it would be. How much charge remains in the capacitor 5.00 microseconds after the circuit is completed? How much charge remains? How much charge remains, you guys? Absolutely, from start to finish. Now you just got to worry about that. That's it. If I asked you how much left, you know that too. Now you're going to plug in the numbers here. What's the charge max? And the whole thing. What is the charge max? Charge max was 7.4 microcoulombs. That's E. Negative is negative. This is 5 microseconds over 7.8 times 10 over 7.8 microseconds. You get the answer. It's going to give you 3.9 microcoulombs. At the end of the day here, guys, you got this. So that right there, what's left, again, this is the one you're using on that one. .9 microcoulombs. By the way, 3.9 microcoulombs, huh? How much left? Didn't we say that the initial charge was 7.4? 7.4 microcoulombs. What's 7.4 microcoulombs minus 3.9 microcoulombs? 3.5 microcoulombs left. They didn't ask us that, but we could have found that in numerous ways. We could have found that here. That will definitely do it. Or just, hey man, just get this answer, which is 3.9 microcoulombs, and subtract it, 3.9 microcoulombs, subtract it from the maximum amount of charge, the 7.4 microcoulombs. 7.4 minus 3.9, 3.5 microcoulombs. And that's it. And that's it. So it would be 7.5, 7.4 microcoulombs rather. 7.4 microcoulombs minus 3.9 microcoulombs would give you 3.5 microcoulombs that left. Nobody asked you that, but if they did, they could. And they could. You know how to answer it. How much left? Not how much is left over on the capacitor. That means how much remains in the capacitor. How much charge has left, has exited the capacitor, so to speak, has gone away from the capacitor, and how much charge is left. Well, if 3.9 microcoulombs is left and 7.4 microcoulombs was the original total, the 3.9 microcoulombs and the 3.5 microcoulombs certainly have to add up. The 3.9 microcoulombs that remain and the 3.5 the 3.9 microcoulombs that remain and the 3.5 microcoulombs that left certainly have to be the total of 7.4 microcoulombs. Okay. Let's look at 71. It is a great problem. Let's talk about it, and that'll be it for that. Again, all of this, or at least for the actual problem discussion of it, is going to scroll at the end of the video. All right, guys, they got, for problem number 71, 3 batteries and 4 resistors are connected in a circuit as shown. What is the current in each of the resistors? That's A. And B, what is the potential difference across the 150 ohm resistor? Okay, so first of all, the answer key is wrong that they have, and that's not the end of the world kind of thing, guys, but it can happen. The answer key that I have looked at that they had, and I think in the back of the book as well, the answers are wrong. The answer key is very likely wrong. We're almost basically pretty sure that it is wrong, because an arithmetic error of sorts is made which throws all the answers in the key off for this particular problem. That can happen when you're solving thousands of problems. Mistakes get made. I mean, we all make them, so that's not the end of the world on that, guys. Things happen sometimes. So let us use the good points of the answer key to make things right, or attempt to do so when we do this. So there's a number of ways you can go here, and I truly a number of ways you can go here. I'm going to go, I'll tell you what I'm going to do. I showed it in one particular way. Let me try to think here, guys. I showed it in one particular way, and they showed it kind of in another way when we did all this. So let me kind of set this up a little bit, if I could, if you don't mind. Give me just 1 minute, guys. I'm going to be back in just 1 second here. Okay, everyone, welcome back. I need to take a little break there, get this set up. This is in your notes as far as the solutions that are provided that are going to be scrolling at the end of the video. It's not going to be written exactly like this. There is another way that it could be done. I'm not exactly thrilled with the other way that it could be done, but it's on there, and we have the solutions are there, and they're valid, and everything's good in that regard. This is a better way to do it, and an even better way to do this is to guess which way the currents are going, and to guess that correctly. You don't have to guess which way the currents are going correctly. It'll show up in the mathematics, but you have to be consistent. Even if you discover that the current's going in the quote-unquote wrong direction because it has a negative sign associated with it, you have to follow the mathematics through and then change everything at the end. Okay, so be very careful with that. So at least you have this on the video. Those that have my class are going to have, that are with me in the courses that I teach, have this as well. Okay, so I'll see, I don't know if I'm going to be able at this juncture, given some of the time constraints, to have this scroll across at the end of the video with everything else. There is a version of 71 in the scrolling that's going to take place, and that should be fine. And what I'm doing here is definitely going to be fine. So pay close attention to this, because I don't know how viable the possibility is of me being able to put this on there with it as well. But we'll see. Let's see if I can get that on there. If I can, it'll be on there. If not, if I cannot get that on there, you have the notes that we have, but you have the video. The best way to do this is to guess which way the currents are going right off the bat. I'm going to purposely, well, I don't know about purposely guess it wrong, but it's sometimes a good thing to guess this stuff wrong and then know how to do it once you've guessed it wrong. The way it's going to end up, if I remember correctly, and maybe it makes the most sense, here's a circuit for you. I've drawn the currents that I'm claiming are going to be present and what direction they're going to be moving as this whole process is taking place. How they're moving, how they meet up, the whole thing. It's looking a lot like at some juncture, all these guys get together and they merge at I1, and then I1 goes across and breaks into the I2, I3, I4, and the I2, I3, I4 add together and they become the I1. That's what I'm claiming. That's fine. As long as we do this and we're consistent with the mathematics, and we know that when we get a negative current and we've done everything correctly, we get a negative current, we just got to reverse the direction of the current. The magnitude should be fine. Okay, true. In some sense, it's almost better to do something like that and still be able to end up on your feet. As I remember the way this thing works out, and maybe it's the most obvious way as well. We'll cross this bridge as we get to it. 60 volts. There's 60 volts. There's 450 volts. There's and 220 volts. So there's a battery with 220 volts. A battery with 450 volts, and a battery with 60 volts. This 450, it certainly makes sense to just fire this thing straight down and see what it does. As it turns out, this 450 fires straight down. This I1 will fire upward, but the I3 and the I4, you can kind of view this 450 volts. That's a lot more than 60 volts, and it's a lot more than 220 volts. This fires straight down. The I1 I2 fires straight down, coming from a huge voltage source, relatively speaking. Fires straight down. There's current, and the current breaks this way, but it also breaks this way and goes up, and it also breaks this way and goes up. So basically, it's doing this. The real big current. That's the real big current. It breaks off into something a little bit smaller, and then it breaks off here, and then it breaks off there. It's actually doing something like that, and this is the real big current. So let me and again, that doesn't even look as dark as it did. Okay, so that's the big current, and these guys, this guy's going to go like this guy's going to go like this, and this guy's going to go like that. So that's kind of, this is your I2. This is your I1, this is your I3, and this is your I4. And this one just seems like, that huge voltage source. This is actually, I think, the way it actually ends up working. And it's not a bad guess to guess something like this. And it turns out, I can look ahead in the notes. I think for certain, the I4 gets reversed. The right way for the I4 is to go up. The right way for the I3 is to go up. The I1 is going the right way, and the I2, coming from that huge voltage source, is coming this way. This guy, and the one to the left of it breaks upward, and these two to the left of the big one here also break upward. And that's the way it should be. We don't know that. I'm telling you the end of the story right now, but that's the way it's going to be. I chose to guess it in a different manner. Can I still get the answer? Can I still answer a lot of questions? And they're asking, what's the voltage across, what's the amount of current across the resistors. I1 is associated with the resistor 120 ohms. I2 is associated with the resistor 50 ohms. I3 is associated with the resistor 90 ohms. And I4 is associated with the resistor 175 ohms. They want us to do something with that as well. All right, let's get to it, guys. A very important problem, very, very fascinating problem. So let's look at it. You saw what I guessed. I already, I sort of, I didn't give you a spoiler alert. I'm telling you, these two are going to be going, this guy's going to be going up and that's going to be going up, and it seems to make more sense that way. But we don't know that. This is what we guessed. And let's see what we can do. Well, you can say a lot of things. Let's develop some equations here and see what we can say here. And I don't know if we're going to do everything word for word on this, but we'll do a lot of this, and I think a lot of it you can walk through once I've given you the setup for it, guys. And let's see what we can say here. For equation number 1, it goes like this. It goes like, let me write it down first and tell you what we're doing. Negative 120 times I1 plus 60 plus 450 plus a negative 50 I2. All those potential drops add up to 0. Those potential gains, potential drops, and all those potentials as you're summing it around there. We're going the far left-hand loop, you guys. What's going on here? How are we doing this? Well, I'm saying there's a current I1. Let's start right here at this corner, I guess you could say, and just work our way around it, I guess. Or let's start right here at this corner. It doesn't really matter. Let's take a walk. It's I1. Everything's okay. I'm not hitting anything. I1 hits this guy and drops I times R. Well, here's R, and it drops I times R. I times R, there's the R. So it's negative 120 I1. That means there's a drop. If you're going with the current, there's a drop. Okay. Current goes through here, there's a drop. Now you go through here, bam. Well, while you're walking through there, you're gaining potential of 60 volts. And that's this. Now you come here, you take a turn, let's go this way. Once you get this way, you're in the I2 realm here. I2 is going to go through here, and you're going to gain 450 volts. Here it is. Then you're going to run down to here and cross the 50. Yeah, it's going to be negative 50 I2. You lose. So that's I1. That's one equation. And how many unknowns? 1, 2. Well, yeah, there's going to be 4 unknowns, you guys. There's I1, I2, I3. You got to remember, at the end of the story, there's I1, I2, I3. So let's go to 2. 2, we write this equation. Forgive me for going backwards on the whole thing here. Let me just write this out and then tell you where it actually came from. 50 I2 plus negative 450 plus negative 220. That's a lot of negatives here. Let's see what's going on here. Okay, we got this. And again, it's a closed loop. It's a closed loop. Somehow, some way, whatever's going on there, there can't be, everybody's got to be accounted for. The equations, all these are simultaneous equations. So let's see what we got here. You can essentially do a lot of stuff here, guys. You can still wind up with the same equation. Now let's start here. Let's take a walk this way. Let's take a walk. The current's going this way, and you're going from a low potential to a high potential, so you gain IR 50 times I2. Using Kirchhoff's rules. You're going through the battery the wrong way, I guess you could say. You're going through the battery in a sense that the battery's not really helping you, it's fighting you. That's what I mean by the wrong way. The battery's fighting you on that one. So it's going to be minus 450. Sounds good to me. Come up here. Come over here. Now go this way. You're going, you're going through here. Yeah, you may be going with the current. That's neither here nor there. you're going across the battery in such a way where you're fighting the battery again. That's negative 220. Come through here and you drop 90 I2, 90 I3. And that's going to be equal to 0. All right. Regardless of how that's traveling, if you're going through a battery in a particular way like that, that's, you're fighting the battery. That's going to be a negative, regardless of you're going with the current or against the current in relation to having done that. Okay. 3. And so let's see how that one goes. I wrote this. I'll just kind of walk you through it. On all of these guys, we're going clockwise. From clockwise around the loops. We chose to go that way. We went this way, clockwise. We went this way, clockwise. We're going to go this way, clockwise. What's going on here? Pretty interesting what's going to go around here. Here there was a drop, here there's going to be a gain. You go this way, and there's other ways you can do this circuit analysis, you guys. And that's something better done in person when we have actually more time, if we do have more time within the context of a course. But let's go this way. You're going from a low potential to a high potential, so you went up in potential because this guy went through. There was a potential drop here, and you're going back up. So it's plus 90 I3. That's why it's coming from there. Here we go again. You're going this way. You're going from here to here. It doesn't really matter how the current's flowing here. Follow the battery. Just what the battery tells you. It doesn't really matter how it's hitting there. Well, you're going this way, it's plus 200. Okay, plus 220 rather, I'm sorry. Come around. Come around here, you're dropping potential because you're going with the current here. That's negative 175 I4, and that's the I4 right here. There's 3 equations right there. Yeah, there's 4 unknowns. That's a little bit of a problem. Tell you what I'm going to do. Let's put a 4th equation. We could put it underneath there, or we could just say this. I2 is kind of the, well, I mean, we know I2 is the big one, but right here we're treating it like it's not the big one. What happens is we're treating it like it's not really the large current. It is, it really is, and we kind of, that's our hunch. But we didn't guess it. We guessed wrong, but that's all right. Let's see what we can do. We got an I4 coming this way, uniting with the I3. The I4 and the I3 unite with the I2, and the I2 plus I3 plus I4 unite, and they're as big as the I1. They form the I1. I1 is the sum of those 3, according to our mathematical scheme, to be discussed, to be determined. I1 is the I2 coming around, meeting up, the I2, the I3, and the I4. Look at how they make the turn. Look at how they make the turn. Makes the turn, links up with this. They both have made the turn, they link up with that. All 3 have made the turn, and they link up with the I. They got to be, what goes in comes out. The I1 is equal to I2 plus I3 plus I4. That is 4 equations. That's 4 equations, ladies and gentlemen, and 4 unknowns. That is essentially the end of the problem. If you know how to solve these equations, these 4 equations and 4 unknowns, how could you do it? Could you use determinants? Yeah, you could. Kramer's rule is beautiful. It works. Beautiful proof to it. There's some intuitive ways to look at it that essentially prove it as well. A little more complicated to look at that way. There's proofs to it. There's intuitive ways to look at Kramer's rule. Some pretty phenomenal mathematics associated with it, and it works. Definitely works. That's it. You solve these 4. There's 4 unknowns: I1, I2, I3, I4. 4 unknowns. There's 4 equations. 4 independent equations in 4 unknowns. End of the story. I have an entire discussion of that. I basically I'll just kind of like walk you through it, and we'll get to it. And I'll have it. Like I said, I'll try to have this I'll try to post, you should, this way I'm doing it here is better than how I did it in the actual notes. So just, like I said, I'll try to have this posted for you guys if it can be done somehow. If not this video, perhaps another video we can do it. So 4 equations and 4 unknowns. You're going to substitute equation 4 for I1. Wherever you see an I1, ladies and gentlemen, you're going to put I2 plus I3 plus I4. Wherever you see an I1, you're going to put the quantity I2 plus I3 plus I4. Where else do I see it? I don't see it anywhere else. Okay, good. Put it up there. Having done that, I1 is gone. I can find out what it is later, but right now I1 is gone. When I put I1, when I put I1 equals I2 plus I3 plus I4, when I put I1 equals that, now I got 3 equations and 3 unknowns. The 3 unknowns now are I2, I3, and I4. And from there, you just, like I said, you can do Cramer's rule at any point or any other way you want to do it, but you set it up. When that's all done, there's some pretty big numbers, divide by 10. Divide by 10 all the way across, and then just proceed to solve the equations, guys. At the end of all of that process, it takes a little bit of time, and like I said, I'm going to try to show some of this, I guess you could say, at some point. So you solve these. When you do that, you conclude that I1 equals, you solve the 4 equations and 4 unknowns. After you get I2, I3, and I4, what do? See, you end up getting I3 and I4 are actually negative numbers in this scheme. That means we guessed wrong. That's okay. We can now guess right. Reverse the direction. Have this guy going upward rather than downward. Have this guy going upward rather than downward. That's fine. Once you even get the negative numbers, though, and you don't like them to be the final answer, I'm okay with that. Don't change anything in the mathematics. Solve everything throughout using those negative numbers. At the very end, then you can reverse the order. Then you reverse the direction in which it's going. Well, I1 is going to be I2 plus I3 plus I4. When you grind it out, it did give you an answer that's positive. It's acceptable, so when we did everything else right. I2 was 6.318 amps. I3, here's where it gets interesting. I3 is negative 3.934 amps. I4, negative 0.766 amps. Everything is right mathematically. And in fact, if you add the negative 0.766 and the negative 3.93, you get negative something on the order of negative 4.7. If you add the negative 4.7 with the positive 6.3, the negative, look, what's a negative 7.66 amps and a negative 3.934 amps? When I add those together, I actually get negative 4.7. I get negative 4.7 amps. Okay, let me add this and this, get negative 4.7 amps, and then add it to this. the negative 4.7 amps plus 6.318 amps is 1.618 amps. Oh yeah, even with the negatives, you do get the right answer, and you do have to keep them there until the end. That's why this stuff works. Okay, that's great. For I3 and I4, we must reverse our initial guess of direction. And like I said, I gave you the, without a spoiler alert, I told you that was going to happen. And our common sense may have said, so let's reverse it. So that's where you get that. Okay, having said all that, go ahead and do it. Follow the rules I told you, though. Okay. All right, guys, we got to reverse that then. That and that. Okay, good. What does that mean? It means this goes up. In reality, the more I draw here, the more I could confuse you if I put my mind to it, I guess, right? This is the reality of it. That should be the I1. That's the reality of it. That should be the I4, and right here, that should be the I3. And now it's reflected there. Do not go adding these now. Oh, this and this. It's 4.7 now. Add it to this. That's 10.018. Wrong. You got to stay with the mathematics all the way throughout until the very end. And then at the end, make the adjustments. Very important. They're saying, what's the potential drop? What's the potential drop across the resistor? Potential drop when following the current. So you're following the current across this resistor. They'd like to know what the potential drop is. Well, the potential drop following the resistor, anytime you're going through the resistor, anytime the current goes through the resistor, there's a potential drop. Anytime the current goes through the resistor, there's a potential drop. So it's IR. I is the amount of current for I4, magnitude-wise, times 175. So for that one right there, all right, the magnitude of the potential drop is going to be what? That's I4 going through there. Either way, don't worry about which way it's going through there. It's going through there. That's I4. I4 goes through there. It's going to be 175 times I4, which is this, 0.766. This is about 3/4. And you can go that way when you want to do something like that, you guys. So 3/4 of something like that. So what are you going to have there? 3/4 of that is going to be somewhere in the ballpark of 134, 135, and they got here 134.05. Remember what I said. Just remember what I said, guys. Be careful, please. I1, I2, I3, I4. Absolutely. This one right here, the potential, the drop, and it's that. Guys, I'll do my best to get this thing scrolling on the video as well. Those of you who have me in my classes, you have access to this through Canvas. So you have this. You have this through Canvas, and that's not an issue. For other people, anybody else who'd want to look at this, I will try to somehow get this on there. If I can't get it on this video, perhaps on another video I can do something like that. But look at it. The main situation is right up here, and you could do a lot to make this work, guys. You could, you're setting the whole thing equal to 0. You know, there's a lot to be said here, guys. Now you could say here, well, how am I going to do Kramer's rule if everybody gets set equal to 0? Well, hold on here. There's a constant and a constant. A constant and a constant, I can get it over here, and it's a non-zero constant over here. Constant and constant, get something over here, non-zero constant over there. Non-zero constant here. As long as they're not all zeros, you can do it. And Kramer's rule is going to work. In regard to something like this, guys, let me just try to look at it, because there's a number of ways Kramer's rule could work. There's just some trivial solutions that could occur if everything's equal to 0. We're not gonna worry about that. Anyway, I will try sooner or later, hopefully sooner, get this to you guys as well in the video format that you can look at it. Those who have me in my in the classes are already going to have access to it. Okay, thank you very much. All the best.